Thank you. Can you see the screen?
Yes, I can see and we can hear you. I think it's great. So
okay.
Thank you very much.
So let me start. Okay, so today I'll be discussing about one of our research works, SST BERT. As told, it was submitted as a part of the Seminole 2020 Task 1, which was dealing with semantic shift tracing. And it was an unsupervised task. So the system name for our system was SST BERT, which is semantic shift tracing by clustering in BERT-based embedding spaces. And we are from the Artificial Intelligence Lab, ITSIA, located in Lucano. So what actually semantic change detection, or otherwise known as semantic shift tracing? So in this task, we have to identify whether the meaning of the sense or the semantics of a particular word changed over a period of time or over different timestamps, multiple timestamps. So if you see in this picture, considering the word cell and the different senses associated with the word cell in the previous century, such as the biological notion of the word cell, the prison or the chamber, etc. And coming to the modern days or nowadays, we have it mostly related to the mobile phones, mobile devices, and the biological notion still exists. But other senses are like fading out, or something has completely lost, the meaning has been lost. So we have to identify this change in the semantics or the meaning or the senses. So coming specifically to the task, so the paper, as I told, it addressed the unsupervised semantic shift tracing challenge, which was a part of Seminole 2020 Task 1, and you can see the details in this particular link. The competition is still open. So you have the leaderboard, you can submit your systems and you can compare it. So the task comprised of two main subtasks. One was the binary clustering, which was termed as subtask 1, and another was ranking. So subtask 1 was simple, like we have to identify whether a particular word gained the semantic or lost it. In general, it's just binary clustering. So we have to see whether the semantics of the word changed or not. In subtask 2, it's a little more challenging because it's more fine. That is, the granularity is more because we have to measure the degree of the lexical semantic change. And by this, what the organizers mean was, if you see this particular example for the word cell, and the three senses of the word cell, like chamber, biology, and phone, and the frequency of the occurrence of these particular senses in, say, corpus C1 and C2, it is obvious that the phone sense is gained because it changes from 0 to 80 based on just frequencies. But at the same time, the sense chamber, even though it has not completely faded off, still it has reduced a lot. So such fine granularity is being measured using subtask 2, which actually rank the target words or the input words based on the degree of the lexical semantic change. So the input for the task was to the corpora. So there were like two timestamps or time periods, corpus C1 and C2, as mentioned, and the target words. And it was done in 4 languages, English, Latin, German, and Swedish. And we have to submit the system for all the languages to participate in the task. So the general method was to use the BERT contextualized embeddings. And as it was an unsupervised task, we used clustering of the contextualized embeddings of the target words, which we obtained from the corpus 1 and 2. And we consider the clusters represents an abstract notion of the sense or the semantics of the words, because BERT is meant to capture some semantics of the word. And we applied a simple k-means clustering approach. And for optimal k-value, we used the Silhouette method. Now, specifically for subtask 1, we had two methods slightly differing from each other. So to explain it, in method 1, we actually combined the corpus C1 and C2 together. We operated on sentence level, so the corpus was divided into sentences. And for the given input target word, for example, the word cell, we extract all the sentences which contain the word cell from these two corpus. So they will be compiled together, and they will be represented using the BERT contextualized embeddings, and the target word embedding, that is the representation for the word cell, will be extracted from each of these sentences. So we assume that that will contribute to identify the senses of this word sense in some way. Now the target word embeddings will be clustered, and each cluster we regard as an equivalence class, giving the abstract notion of the sense or the semantics of the word. Now, once the clusters are obtained, we have to see whether the cluster is pure or impure. So this means that we see how many sentences or how many elements in that particular cluster belong to corpus C1 and C2. So if the cluster contains the elements belonging to both the corpus, it means it is impure. So if all the clusters are impure, it means that there was no semantic change. So in the case if one particular cluster was pure, it means either essence is gained. So if that all the elements belong to C1 and there is no element belonging to C2, then it means essence was lost. Vice versa, it means essence was gained. So that was the general notion. And in method M2, we used a very simple approach. We actually consider the corpus C1 and C2 separately and cluster the vectors separately. And we just consider the mapping between the clusters using Hungarian algorithm and actually see the number of clusters were same, like if they were matched at both the ends. Now for subtask 2, that is the ranking, for both method 1 and method 2, we used the same approach. So we used here the Jensen-Shannon distance in order to measure the differences in the probability mass functions between the frequency distributions obtained from the two corpus. So the frequency distribution means we just take the counts of the elements in the cluster for each corpus C1 and C2. We make it normalized and we just compute the Shannon distance and then rank the target words based on the distance value. So this is how subtask 2 was carried out. Now I will directly jump into the results. So sorry. So for the subtask 1, the proposed methods were outperforming the baselines provided by the semi-val contest. So mainly 3 baselines were provided, which were either based on frequency, normal frequency distributions, or like a random baseline, sorry, always predicting a majority class, or simply representing them into vectors and taking their alignment and then calculating the cosine distance. So they were simple baselines. And the approach outperformed all the baselines. And we found that method 1 was best for German and Swedish, while method 2 was best for English. Latin was more challenging. In the sense, based on our approach also, and in the complete task also, we found that it was more hard to tackle Latin language. And for subtask 2 also, the results were quite dependent on the corpus or the language. And if you can see the table, overall, comparing method 1 and method 2 actually outperformed method 1, and also all the semi-eval baselines. And in the overall comparison with all the other systems, our system was like in top 5. In subtask 1, while in subtask 2 we were like in the 15th position, I guess. So there require some improvement, quite a lot of improvement in the ranking part, which is quite challenging. And also it was quite interesting to note that in most cases, the good results in subtask 1 was not quite correlated with like the good results in subtask 2, even for other participating teams. So this is like just a visualization of the clustering that we did, the TSNE projection. So for the target word tip in the English corpora, so the colors represent the clusters. So you can see there are 2 clusters, and the slight difference in the shape, I think you can note it. One is filled, the other one is not filled. So they represent to which particular corpus these elements belong to. You can see that there are 2 clusters, and one cluster is quite big, the orange one, and it is quite impure. I mean, you can see the elements belong to both the corpus. Well, the second one, blue, is very small. And if you can see, I don't know, like here, there is like only one element which falls into C1, corpus C1. All other elements were into C2. So actually in the task, they define some thresholds which we have to consider to decide whether the particular target word gained or lost the census. And it was also language dependent, like for each language, they gave a different threshold. And based on that, this falls into the category of there is a semantic sense change. Now, another result, so this is with a second method where we use the Hungarian matching algorithm. So you can see here for the word lane, there are like 3 clusters obtained. So obviously for both the corpus, we had 3 clusters matching. So it means that there was no change in sense for this particular word lane according to method 2, and it was correct. So yeah, these are some of the visualizations. So yeah, this was like a preliminary approach from our part to participate in this challenge of unsupervised detection of semantic change detection of the words. It's quite challenging, and we have seen like approaches used by different people, not only like transformer-based models or context-dependent models. There were actually context-free models which used like word-to-vec models which outperform the context-dependent models. And of course, as I told, in the ranking also, we have to see, we actually, I mean, our notion was that if it performed well in subtask 1, it should have performed well in subtask 2, but that was not the case. So these relations have to be analyzed, and this will be done in the future. And again, the linguistic peculiarities of different corpora would also be interesting to investigate. Now, for more details, you can go to this particular link here, which is actually the main project. And they are organizing these different shared tasks. They have one shared task, I think, which was in ASIAL 2021 also. Yeah, but we could not participate in that. So you can see the code is freely released for our particular system, and you can see our paper also. Okay, so that's all from my part. Thank you.
Thank you very much. So I have a very quick announcement. So since I've got informed that the next talk should start at 15:15. So we have ample time for question now. And so maybe to warm us up, I will start quickly. So I have a short question about kind of clustering of contextual embeddings in general. So have you tried out like different norms, or like is kind of L2 norm the most, the best one, or can you maybe give a comment on that?
No, actually we didn't. We just tried the L2 norm, and I mean, when we started off, we just tried with the pre-trained BERT modeling provided by Hugging Face model for English, and the multilingual BERT model for the other 3 languages. But of course, we would also like to try with maybe sentence transformers. I like SBERT, which is, which use the Siamese BERT model, and I think which could give maybe better representations. And as I told, again, even though it is like we assume that context-dependent representations would help us to capture semantics or senses more, like many systems which participated in the challenge and used and compared like word-to-vec and BERT models, is so that word-to-vec models were performing better in this particular challenge.
And I see here in the chat there was another very interesting question. So Leandro asks, have you used a monolingual model for each language or a multilingual model for all models? Does your method work with cross-lingual embeddings?
So as I told, we used the multilingual BERT model for the 3 languages, German, Spanish, Swedish, and Latin. For English, we used the monolingual BERT model. Yeah, and actually there was one system which used the XLM model, and it was performing well, like almost similar to our results, but again, in the ranking task, it was not performing better than us.
Thank you very much.
Thank you.
So, are there more questions from the audience? At this point, I would also maybe invite you to turn on your cameras so our speakers can talk to some friendly faces.
Oh, I'm sorry.
No worries. I meant in general.
Is it okay? Can you? Yeah.
And I will see some more friendly faces. Thank you very much.
Yeah, it's quite important in this situation.
Yeah, I should have mentioned it earlier. So, I mean, of course, if anyone has questions, you're also free to ask them directly, like just speak up. I think we're not too many people at the moment, so no need to raise hands or anything.
And of course, suggestions are also welcome, like how to improve, like if you have some ideas. Like anyway, we are planning to continue our research in this topic, which is quite interesting in the linguistic domain, especially in historical, analyzing historical documents.
Yeah, so I mean, I think you mentioned that like Latin seemed very difficult.
Yeah.
Maybe you can like elaborate a little on that. Like, well, like, do you have an idea why it was particularly hard compared to the other ones?
Yeah, I mean, yeah, actually not even in the system description paper, finally, like when the organizers were analyzing all the results, they were just telling like, okay, Latin was quite challenging to detect. Yeah, and I mean, I'm not sure, like if it was like a supervised task, we could say about the training data, the amount or something, but it was unsupervised. So maybe that's why we are also interested to analyze the linguistic features, like focusing on each particular language, which may throw some light.
Yeah, definitely. I mean, if you want to kind of, I mean, I feel like Latin is kind of a litmus test when you want to apply it to any sort of historical documents or like low resource or relatively low resource languages. So that would be definitely interesting to find out.
Yeah. And also, I mean, I don't know how BERT multilingual model actually, what is its efficacy in dealing with such languages.
Yes. So maybe is someone aware whether a BERT, like multilingual BERT per default even includes Latin? Maybe that's one source of problems.